second talk, we're very happy to have Zihan. He's going to tell us about exact tidal and anomalous dimensions with applications in Waveform.
Right, thank you very much for inviting me to this nice conference and this beautiful island. I'm so happy to be here. And today my talk will be about exact tidal anomalous dimensions with applications in waveform modeling. So essentially, I will tell you anything I know about logarithmic divergences. All right, so the talk will be based on these 3 papers. And also, thank you to all of my excellent collaborators. Fabian is here, Misha is here, and also Julio is here. So the main results from this from the talk will be based on some unpublished results. All right. So we all know that this decade is the golden time to study black hole physics. So the current status from observation that we have over 200 events in total from LIGO, Virgo, and Caragra collaborations. So now, from a theoretical perspective, let me introduce you guys to the trail of studying black hole dynamics. So we have in total 3 communities. The first one is the post-Newtonian effective field series, which makes manifest of the expansion we oversee. The second community is all we are here is scattering amplitudes, which makes manifest of the weak field expansion. The expansion assumes that G is small. The third one is a little bit like old-fashioned, but actually we can learn a lot from that. It's called black hole perturbation theory. And basically, it makes manifest the expansion of the cell force, which assumes that there are some point particles orbiting around a big black hole. So it's the expansion around mass ratios. And today, I will focus on some intersection regime, which, if you are familiar with the chamber music, it's called the trails. So today, basically, I will tell you how to play the trail in black hole physics. All right. So we already heard a lot of talks, very great talks, in how amplitude people can help us understand black hole perturbations or even the waveforms, especially the wonderful talks from Julio, Mikhail, and maybe later from Julia is around this kind of areas. But I will focus on another perspective, like how GR people or how black hole perturbation theory helps you to understand the amplitude and the waveforms. So a brief recap about what is tidal effect. So the tidal effect is actually captures the deformation of some compact object within the background, within the field, within the external gravitational field, basically. So it's the most simplest effective field theory maybe you have learned in your life. It's just the multipolar expansions. So the action is just the quadrupole. Electric quadrupole comes to the external electric field, and the magnetic one similarly. So one thing that we learned from astrophysical people is that the microscopic degree of freedom for the quadrupole moments of some compact stars is actually the so-called Lagrangian fluid displacement. And this is basically once you solve the stellar fluid equations, you can basically extract the quadrupole moments of some compact stars. Also, when we do the study of tidal response, we use the linear response theory. So the quadrupole moments can be written as some Wilson coefficient and then some tidal response because of the external dynamics of the electric fields. The leading one is well known to be the static tidal love numbers, which scales with radius to the 5th power. And you can do more generally for other multipolar moments. It scales with radius to the 2L plus 1. L is the multipolar index. And you can do the Taylor expansion of the called response function. So the next leading order is some deceptive contributions, which we call dissipation numbers. And it scales with radius to the 6th power times some viscosity. So this new here is actually known to the fluid people called kinematic viscosity. And we studied some of these regimes for neutron stars. In some extremal equation state, this viscosity can compare with the black holes can be order 1. So there can be some contributions to some neutron stars in extremal cases. All right. So, but from a theoretical perspective, there are also a lot of interesting questions we want to understand from effective field theories, especially the logarithmic divergences. Because we know that if we couple point particle to the Einstein gravity, this theory is not renormalizable. So we expect some UV divergences. And first of all, there are 2 types of divergences we can study. For tidal effects, as you can see, we are sending some waves to the star oscillates and then radiates the wave again. So we know that GR is nonlinear, so you need to attach some mass insertions in this context. Basically, the outgoing waves got backscattered by the background magic. But so here I just draw the two-loop diagrams. You can go even higher order. So this is known to the EFT people as renormalization for the correlation functions. So in QFT sense, it's called wave functional renormalization. And so the question is, can one extract the anomalous dimension here? It's a big problem. This is very important because if you start the wave radiation from a binary, you expect similar things to happen. You just replace tidal particle with a radiative particle, and you just replace the mass insertions with the conservative binding energies. So you expect a similar logarithmic divergence to happen here. So to understand these logs is very important because these logs will appear in the waveform as the tail effects, and that's the main obstruction when people try to do the analytic continuation for the boundary to bound maps. All right, so today I will try to tell you our ideas on how to resolve this problem based on black hole perturbation theory. So I will focus on these 4 parts. The first one, I will tell you some analytic structures in black hole perturbations. It's called near-far factorization. And the second, I will show you my experience in discovery of some exact Beta functions which seldom exist in physics. The third one, I will tell you how we prove this non-perturbatively. Then we will tell you some of our initial trials on the waveform resummation. All right, so the EFT part, as what Julio said on Monday, we're trying to study the so-called gravitational Raman amplitude. So basically, we first write down the effective action is the point particle, the mass coupled to the proper time, and you need to add the bulk Einstein gravity. And to higher order multipolar moments, you insert the tidal operators. So essentially, we have some elastic part. You're sending some waves to the black holes or neutron stars. Then you got scattered by 1/r potential. And you can do this iterative ladders, or get scattered by 1/r² potential, things like that. But at certain high orders, you will see the response of the compact object comes in. Also, if you use optical theorems, you can see that the binary part of this amplitude will tell you the absorption cross-sections. But from black hole perturbation theory, we start from in a different perspective. We are sending some waves in the black hole background. Okay, some crazy things happens in the middle. It's here. And some of the waves goes into the horizon. Some of the waves goes reflected back to infinity. So we are trying to solve this problem. I will now discuss how to solve Tarkovsky equations. This equation is called Tarkovsky equation. I will not show you how to solve it exactly, just to show you the final result. So this is basically the ratio of the wave amplitude in the equation. It's related to the scattering phase shift and the absorption probability. So it factorizes manifestly into this near zone and the far zone part. So the far zone part, from the equation from the differential equation perspective, the convergence radius, it converges at infinity, but it diverges at horizon. So it knows nothing about horizon. For the near zone part, it converges at the horizon, but diverges at infinity. So it captures the tidal response of the compact object. And these two terms exactly factorizes. So here, the most important parameter that we are related to the later part of my talk is the so-called Floquet exponent. So if you're familiar with the second order ODE, some asymptotic structures around singular points is characterized by this Floquet exponent. This will be later super important. So this is an exact formula. And then what can we learn from that? It's actually, first I will talk about the far zone physics. So the first point is that far zone describes the black holes in a spinning point particle limit. So it knows nothing about horizon. And the second point is far zone is purely elastic. This is very obvious because it knows nothing about horizon, so there's no absorptions. And so the third point is very important because there used to be some confusions about this analyticity stuff. So far zone phase shift is polynomial in terms of black hole spins. This is aligns with the EFT estimation that you can do spin-induced multipolar expansions. And the second part, the next one is very mysterious actually. So there are some class of special functions. It's called the Nekrasov flexibility function. It's something appears in 2D conformal field series that somehow enters into black hole perturbation series. And you see that this special class of function resounds or post Minkowski expansions. So this is very interesting. And we also know something about near-dome physics. So the near-dome physics is the following, that you have the exact tidal response function, which I wrote it here. It's made up of a bunch of gamma functions, which in the extreme black hole limit, near horizon limit, you can understand it from ADS-CFT. And the cool point is that this response function is not analytic in G, because in general, this Foucault number or the characteristic exponent is some fractional numbers, so it's not analytic. It also tells you that if you want to do diagrammatic analysis, you cannot. It's not possible to know anything about the black hole horizon. And the black hole horizon contains absorptions, as expected. Also, if you look at the pole of the scattering amplitude, because this is the exact formula, you also know the quantization condition for quasi-normal modes. This is what Victor talked about us in the morning. All right. So now let's try to do some perturbative analysis. So perturbative analysis, the near-dome part has these very simple structures. So it scales with gm omega to the 2 nu plus 1. This nu is just some Foucault number. And for the people who is familiar with black hole perturbation theory, or for GR people, this is historically known as renormalized angular momentum. It's a very interesting parameter. It's also very universal because you can do similar analysis for relativistic stars, like neutron stars. You will see that the scaling power is exactly the same. So it has not. So it's universal for all kinds of spherical compact objects. That's why it's very important to understand what's the physical meaning for this renormalized angular momentum. Actually, this parameter was named by some Japanese people back like 30 years ago around. So there was a famous paper, which is the initial attempt to solve the Minkowski equation exactly. And this parameter was introduced there as the characteristic exponents. And this method is called MST method, has been widely used in the waveform modeling and in cell force calculations. But some mysterious happens that it was super unclear for the PHPT people. They don't know what's the physical meaning for this parameter for almost 30 years. So today I will first tell you like how we address this problem. What's the physical meaning for this renormalized angular momentum, whether it's just a fancy name or it's renormalized something. So the derivation is actually just 5 lines. I come up with one night before I went to bed. So actually, it's very simple. That you can start with dimensional analysis. The lump number scales with radius to the 2L plus 1, as I just said. Also, you can do Newtonian analysis. The scattering phase shift from tidal responses scales with radius times omega to the 2L plus 1. In GR, as I just showed you, it will be R omega to the 2 nu plus 1. So just these small differences, then some algebraic games, and you rewrite R omega to the 2 nu plus 1 as this simple form, then you start to see something mysterious happens. That if you understand mu over omega to some of this power as loop corrections, then the previous one will be something like a renormalization. But now it's still unclear. It's just some argument. So I wrote down like these RG equations, but at this point, it's we are still not sure what it renormalize. But something about renormalization happens. Then we do some comparison. That if we compute perturbatively the tidal response by doing Feynman integrals, people have found that the 2 p.m. corrections, it's like the anomalous dimension is written here, computed by actually first time by Goldberg and Ross. And some people are very brave, compute the 4 loop corrections, but I don't see any results on 6 loops. But it seems that the 2 loop and 4 loop result all perfectly matches this renormalized angular momentum. So now we're very confident that renormalized angular momentum is not just a fancy name. It indeed renormalized the UV divergence that appears in the tidal response. So let me first draw my first conclusion. I think it's very important because it answers a 30-year-old question in black hole perturbation theory. The renormalized angular momentum, mathematically known as characteristic exponents of Floquet number, can be understood as an anomalous dimension for tidal operators, which accounts for all of these tail effects. It's very interesting because in black hole perturbation theory, we have recursion formula to solve this to all orders. You can even do numerically. So this resounds tails in a magic way. But what is the implications for the radiative multiples or for waveforms? So we need to prove this formula in a more general settings. So let me tell you the whole idea. Is that so the conclusion is that the anomalous dimension for radiative multiples can be also written in a very compact form. It's related to the scattering phase shift or the competent phase shift against the binary of the compact object, the binary compact object. So basically, you try to imagine that you scatter some waves against the binary. If you are powerful enough to compute the scattering phase shift, you now know the anomalous dimension. So the proof is actually not so difficult. That we follow a paper by Simon. And so basically, we start by introducing, constructing some in observables. So the tidal operator Q dot E, we treat it as a local in time, local in space operator. And you can study the matrix element is actually some of this some waves radiated from the multiple, got scattered by the far zone of the binary object. And there will be some nonlinear interactions, and the waves travel to infinity. So by constructing this in observable, we see that it's called symmetric correlator, and it's manifestly time reversal invariant because we couple this omega and minus omega equal footing here. And then the idea is that we can do some rotations. If we do a dilation rotation for this correlation function, we see that we will enters because it only has the logarithmic divergences. So if we do a rotation by a factor of I e to the I pi on the omega, because of time reversal symmetry, the whole correlation function rotates as a factor of 2 pi. So you end up in another side of the branch cut, which picks the complex conjugate of the correlation function. Then you try to make use of this unitarity in scattering matrix. You will see that the complex conjugate, the Hermitian conjugate of this operator O can be closely written as the scattering or the phase of the S matrix for the scatterings against the far zone of the binary. Then from this analysis, you can get that the anomalous dimension for the tidal operators can be written in this in a closed form. Here. So basically, once we know, if we are powerful enough, we know the scattering phase shift against the binary, we know the exact anomalous dimension for the radiative particle movements. Now, let's take some simple example. So if we only have this energy insertions, basically, so energy is once you integrate out the potential modes of the binary, you just replace the mass of the compact object with the conserved binding energy of the compact object. And in this limit, we know that because of the Brinkhoff theorems in GR, like if you have these energy insertions to all orders, but linear order in spin, the metric is universal. So the far zone of any compact object is universal. Then we can use the Kerr result to extract the anomalous dimension. And we explicitly check that indeed, if we know the anomalous dimension for Kerr, then we can know the anomalous dimension for radiative particles to all orders in G. This is some non-perturbed result. You can solve these equations even numerically. And so now, the point I want to make is that for many observables, like including waveforms, we all know that there has been proposals of B2B maps, boundary to bound maps, but this all breaks down when we have tail effects. So people need to compute tail effects from other ways. And here we provide you the way, and the way to go is to compute the competent scattering against the binary. Then you know everything about tail effects. So this formula essentially, I think, it provides boundary to bound maps for the tail effects. Also, we also try to make some connections with the true waveform from like the gravitational radiation from for the inspiral problem. It's not a scattering problem, it's a truly inspiral problem. So Damour actually proposed some factorized waveform formula. It's called the multipolar post-Minkowskian waveform. So the first term is the conserved energy, the UB conserved energy in the geodesic limit. It's just the energy of the point particle. And here T is the resummation for the tail contributions, basically all the logs. And then there will be some phase modulation and the amplitude modulation based on post-Newtonian and post-Minkowskian series. Damour actually wrote down a gas formula for this tail resummation. Then, so there are two factors. First is S. S is actually known in dark matter physics as a Sommerfeld enhancement factor. So basically, it resums all the leading singularities due to the IR divergences. And the phase is actually the scattering phase, or people call it the Weinberg phase, because you're scattering against the 1/r potential. So there are some logarithmic divergences. Now, because we just know that the renormalized angular momentum is also something universal. It knows about the subleading corrections from the far zone. So the game to play is you just replace L with nu. Then you can get more things resolved. So here is our proposed formula. The first S is the improved Sommerfeld enhancement factor. Then we also add more terms into the tail corrections. And the key important thing is that we also add like this logarithmic terms, which comes from the solutions of the RG equation. Let's see whether we are on the good stage or no. That we go to the probe limit, and we find, okay, our proposal is all correct. And we try to go even beyond the probe limit. Then we find that all of these terms about pi's, about logs, seems to be like we can all resum it. So first thing you need to check that this proposal seems to be correct. And there are some open questions that something that we still don't understand, and we'll try to understand it. The first question is that we all know this renormalized angular momentum only resolves to terms that is linear in angular momentum. Because if you go to angular momentum square, you don't have a universal like metric for the compact object. So it will be good if someone can compute these kind of things, that the anomalous dimension for this Q will be given by the constant amplitude against the binary with the L square insertion and the energy insertion like here. Or it's also interesting to study the tail effect or tail of memory. So memory, it means that you have a quadrupole radiation, then you like the two quadrupole radiation like hit each other in the middle. So there are some nonlinear interactions from the radiations. And the tail is just you get another like mass insertion in the wall line, and you got some enhancement or logarithmic divergence because of the IR effect. Also, it will be interesting for someone to study, understand this from the constant amplitude against the binary. It will be related to the quadrupole insertion, generic quadrupole insertions with the energy tails. Also, it will be interesting to understand the analytic structures of renormalized angular momentum by doing more numerics or try to understand from some magic ways. This is currently we don't really know. Also, it will be interesting to compare our proposed tail resummation with the calibrated UV waveform or numerical relativity. Okay, so let me summarize. So in my talk, I basically made 4 points. The first one is that renormalized angular momentum in black hole perturbation theory gives some exact anomalous dimension, which corresponds to the tail effects in waveforms. Also, the binary Compton scattering phase shift should give us more general running of radiative multipoles. And we have proposed a new factorized and partially resummed multipolar post-Minkowskian waveform. Maybe we can do even better. Also, we welcome all you guys to join us in finding more connections between black hole perturbation theory, amplitudes, and maybe with the help of post-Newtonian post-Minkowskian force, effective field theory, and also mathematicians. All right, thank you.
Questions for Zihan?
thanks for the really nice talk. So yeah, about this tail effect. So how does your understanding compare to like previous work? That was a work this year on this tail effect. I thought it was more like the post-Newtonian approach. So I'm trying to understand like how much is left to do for this to solve this tail effect completely, this open problem. How does it advance what we knew before?
Sorry, can you see it like more split? More
Yes, I'm just trying to understand. So this, you're saying that now basically we can continue this waveform to the bound regime. Can we do it completely or just some part of it? Or like, is there a clear path now to try to do it completely?
Yeah, so the proposal here, we only work for the distributive sectors. For conservative sectors, we have no idea. This only works for like energy flux waveforms. I think it works. For conservative sectors, it's still hard to say.
Okay, more questions?
Maybe just a quick clarification. So for the anomalous dimension formula, the delta there, which phase shifts is this?
Or it's called the Faraday shift against the binaries. Basically, do a Compton, but not for a single object, but for binary. Instead phase shift, then you can use this formula to estimate the anomalous dimension.
And show the effective action. Scattering against this.
Yeah, against the
point
binary
multiple,
object.
with generic multiples.
Can I ask, but yeah, I was confused because in this sense, what's the so when you say Compton, there's an incoming wave, right? But precisely in this diagram, there's no incoming wave.
Yeah, so basically, you can just put a cut on the legs here. See the Compton against the binary.
Okay, we have time for maybe one or two more questions quickly. Okay, no more questions? And let's thank Zihan again.